Hello, this is Nikita Takulkar, and this is my Physics 2 Lab number 4, Magnetic Braking with Faraday. The purpose of this lab is to explore Faraday's law, which basically explains how an electromotive force in a conductor is induced through a changing magnetic field. In this case, our changing magnetic field is going to be a falling magnet, and it's going to be falling through an inducing current in a tube of aluminum foil, and we're going to explore and model this using Newton's second law, Faraday's law, and the Biot-Savart law. Just a quick preview of the results. The experimental time for the falling magnet was 1.254 seconds, while the computational time was 1.225 seconds. In this lab, we'll be using the update formula version of Newton's second law to essentially help with our closed grip code, but most importantly, we'll be using Faraday's law, which talks about how changing magnetic flux through a loop induces an electromotive force in the loop, with the current opposing the change in flux. This last part right here, the opposing part, would be Lenz's law, and that's responsible for the negative n in here. For the EMF to equal negative the number of loops times d phi d theta. Phi, of course, is current times the surface area times cosine theta of the angle made. We'll also be using the Biot-Savart law, which describes how the generated magnetic field is related to the magnitude, direction, length, and distance of an electric current. We have some quick initial conditions here. The tube length is 0.3 meters, the tube width was 0.005 meters, inner radius, outer radius. The magnet mass is 0.024 kilograms. The magnet nu, which is from the previous lab 3, was 5.5 am squared. And finally, after dropping the magnet through the tube 5 times, we came out with an average of 1.254 seconds. Just some checkpoint questions before moving on with the glow strip code. Our system, of course, is the falling magnet. The surroundings were everything else, the aluminum tube, the phone with the magnetometer used to orient the magnet, the table, everything else would be in the surroundings. So, question number 1, why can't we use a ferrous tube? Well, ferrous metals have iron, and the magnet would be attracted to the tube because it's attracted to iron and other ferrous metals, and this would either just have the magnet latch on to the tube or skew our measurements and results in some way by its magnetic force. So we can't use a ferrous tube. Next, what happens to the magnet inside the tube in comparison to the magnet falling in free space? Well, inside the aluminum foil tube, because of the induced fields and the induced current, the magnet falls slower than it would in regular free space. So it's basically being slowed down by the magnetic field, and that's why the time is a little bit smaller than when it would be just dropped in midair. Now we get to the simulation portion of our experiment using our glow script code. Right here in part 1 is just us setting up our initial conditions right here. And then we have calculating the magnetic field at a position R relative to the bar magnet using the Biot-Savart law. Then we calculate the rate of change of magnetic flux through each ring caused by the falling magnet right here. And we also use Faraday's law over here in step 4 to calculate the current induced in each ring by the falling magnet. Then here in steps 5 and 6 is when we're using the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet. And then right here, part 6, would be using Newton's third law to calculate the force exerted on the falling magnet by the entire tube. Finally, down here, we're going to get to step 7, which is essentially just the net force, which would be the magnetic force that we just calculated right here, plus just adding gravity to that. And finally, we're using Newton's second law to update the position and velocity in the code so that we can have a graph formed right here. So in this graph, in the beginning and end, we've got a steep slope where the gravitational force is the strongest thing that is being felt by the magnet. But in the middle here, where it flattens out, that is when the magnetic force and the gravitational force are equal. And finally, down here at the very, very bottom, we can see that we have a computational time of 1.225 seconds, which is, again, slightly faster than what we found in the experimental model. So, interpreting the simulation, we know that red is counterclockwise and blue is clockwise. If the magnet is flipped, the directions of the induced currents will reverse, but of course the magnet will still fall. And of course, we just noticed that the computational time is faster because it doesn't include things like air resistance or human timing. And we already talked about the graph's shape and why it is the way it is. Possible sources of error in this experiment, we didn't include things like air resistance and also friction from sometimes the magnet hitting the side of the tube, so that could be factored in. Also, the magnet's fall was timed using me and the timer app on my phone, so of course that could lead to human error. Finally, the discussion questions. What if the tube resistivity was near zero? Well, that leads to stronger induced currents, more intense magnetic field, so the magnet would fall slower. If there were holes in the tube, it would interrupt the induced currents, interrupting the field, so the magnet would fall faster.